Hello all, welcome to Windows Assembly Language Primer for Hackers video series. Now this series is a natural continuation of the Assembly Language Primer for Hackers video series, which is already there on SecurityTube. In that video series, we concentrated on the Linux platform to learn assembly language. In this one, we will look at the Windows platform. So in part 1 of this series, we will try and understand processor modes typically. So what is the agenda? First, we'll have a quick introduction and prerequisites. Then we'll look at various different processor modes, look at real mode operation in more depth, then understand the syntactual difference between AT&T and Intel modes for assembly. And then finally, we will end part 1 with a customary Hello World program written in assembly. So what is the objective of this video series? Well, the whole idea is to learn assembly language programming both in DOS as well as in Windows. And you should be able to write simple Windows programs in assembly after this series. Also in the end, we will look at how to disassemble simple programs to understand how they work. So where will this series be used? The way I view it is that this series will be a prerequisite for learning reverse engineering, exploit writing, understanding viruses and worms, and a couple of other topics which require you to understand low-level details of how code works. The prerequisite for this course is the Assembly Language Primer for Hackers video series on SecurityTube. Now we will build on the above video series and add more details but specific to Windows. We've covered the basics of registers, instruction sets, little bit of debugging, etc. in the Assembly Language Primer. This is the link for people who have not seen the Assembly Language Primer. Please view that video series before you start this one. Else you may be lost because there are a couple of basic things which I've already covered there, which I'm not going to repeat in this video series. Okay, so let's start. First, we'll try and understand memory models. In this, we'll look at two different models. One is the flat memory model and the other is segmented memory model. So what is flat memory model? Well, in this case, memory is laid out contiguously. What we mean by that is address 0, 1, 2, 3, so on and so forth till address n are laid out linearly, one after the other. Now, in case of Intel architecture 32 processors, or the IA32 as they are popularly called, the value of n is 2 to the power 32 minus 1. So we start from address value all zeros to 2 to the power 32 minus 1. Of course, the huge advantage of this model is that it is very easy to address any part of memory by the processor. Then we have the segmented memory model, which is somewhat a bit more complex, but is very useful when it comes to running modern operating systems like XP, Vista, etc. In this case, memory is divided into various segments. Now, what happens is that we have something called a segment selector, using which an appropriate segment is selected. Within that segment, we use an offset to actually figure out the exact memory location we want to deal with. Now, using these segments and offsets, we can go ahead and address any memory within the available memory space. We will come back to segmented memory models later on when we talk about protected mode operation of the processor. Okay, so let's revisit processors. Now, the number of address lines in the CPU determines the amount of addressable memory space the processor has. Now, in older families, which is the 8086 and the 8088, they had 20 lines, address lines, because of which they could only address 2 to the power 20, which is 1 MB of memory. 80286 onwards, there were 24 lines, and this could access 2 to the power 24, which is 16 MB of memory. Now, if you're unclear about what is CPU, memory, the data bus, control bus, address lines, etc., this would mean you'd have to revise the assembly language primer for hackers. The link was provided a couple of slides back. We've discussed all of this in depth in that primer. Moving on, more address lines typically means more memory access. Now 80386 onwards, there were 32 address lines. This allowed access for 2 to the power 32 memory spaces of 1 byte each. 2 to the power 32 is 4 GB. Now all Intel processors which support 32 address lines are referred to as the IA32 processor family. Now even after this, when we reached Pentium Pro processor, 4 additional address lines were added, and this made the total to 36 addressable lines. Now hence the total addressable space became 2 to the power 32 plus 4, which is 2 to the power 36, which is 64 GB. Now this extension of these 4 additional address lines, and which actually gives the processor the ability to address 64 GB, is called physical address extension, and the short form is PAE. This is the abbreviation, right? Now let's look at processor modes. Now processors have the capability of operating in different modes. The first is real mode. This is typically where you have 16-bit registers and a 20-bit address line. Protected mode is typically when the processor operates using the 32-bit address lines and segmented memory. So there's a lot of interesting things. Even real mode actually uses a very simple form of segmentation. Protected mode actually uses something much more complicated. We'll get into that a bit later. Virtual 8086 mode is something which actually allows real mode programs to run within protected mode. Now this comes in handy when you want to run DOS programs, let's say within Windows, right? We'll look at this later. Finally, we have the system management mode, or SMM as it is popularly called. Now this is typically used most of the times to do debugging of problems in chips. What we typically do is, the whole idea is to actually run code from some sort of a firmware or hardware device. Now we'll not be discussing this in much depth. Later on when we talk about rootkits, probably in another video series, we may talk about SMM level rootkits, right? So 4 different operational modes. For our discussion, we will primarily look at the real mode and the protected mode. So what is the real mode? Well, as mentioned previously, in real mode basically is a 16-bit execution environment in which all registers are of size 16-bit. Also, real mode uses segmented memory and has a 20-bit addressing space using 2 16-bit registers. Now the most popular operating system which runs in real mode is MS-DOS, which I think all of us are familiar with. This is the Microsoft Disk Operating System, as it is called. So how, using 2 16-bit registers, are we able to address 20 bits of address space? Well, we do a little trick. What happens is, let's take an example. Let's say the 2 registers, CS, the code segment, as well as the IP register, contains 2 16-bit values using which you want to get to an actual linear address, right? So the contents of the CS register goes into what is called the segment address, and the contents of the IP register or the instruction pointer goes into the offset address. Now the trick of actually enabling 20-bit addressing space is to shift the segment address to the left and actually add 4 bits of zeros. So basically, if you think about it, we've shifted the segment address by 4 bits. Now this gives us what is called the segment base address. Now what we do is then we add the offset address to the segment base address to get the linear address. Now this is the actual address which is used to address the 20-bit addressing space. Let's take an example. let's say the CS or the code segment had the value 07C0 in it, and let's say IP had the value 0008 in it, right? So what we do is we add an additional 4 bits here, which is just an additional 0. That makes it 07C00. Then we add 0008 to it. Now if you notice, this would give you 0x7C08 as the actual address. Right, so is this clear? Now let's take up another example to make this more clear. Let's say the CS has 16 bits having the value A000. Now we add an additional 4-bit 0 here, and let's say if the contents of IP were 5F00, then let's just do a simple linear addition. What happens here, we have an additional 0 for the 4 bits. It gets added, comes out as 0. This column gives us another 0. This column gives us an F. This column gives us a 5. And this column gives us A. Hence the addition basically spans 20 bits and has the value A5F00. Right, so this is how, using segment and offset in real mode, which are each just 16 bits long, we are able to address a 20-bit memory space. Now MS-DOS real mode operation, as we already mentioned, all the CPU registers are 16-bit. One of the downsides is that there is no memory protection, which means any DOS program can write anywhere. It can even overwrite critical parts of the MS-DOS operating system and crash the machine. This is one of the key drawbacks of real mode operation. Now we can inspect the memory using a utility called mem.exe in real mode. Let's look at this utility. Now I have a command prompt open, and if I just type in mem, I actually see some synopsis of the memory. Now it actually gives me some details, but in order to get a very good overview, we basically run mem with the debug switch on. This gives us a lot of information. Let's start from the top. So this gives us the entire address layout starting from 0, which is from low memory to high memory. And as we can see, in low memory, basically the operating system critical parts are loaded. So first we see the interrupt vector table, which is loaded. Then we have the ROM and the DOS communication area. From there on, you have device drivers which have been loaded. You can see the LPT and COM ports, etc. for communication with these ports. And then you have a bunch of other things which are useful for DOS, right? So typically you have IO specific things, KBDs for keyboard, mouse, so on and so forth, right? So this is how memory is laid out in real mode. Now the issue is, if you ran a real mode program, it could go ahead and easily corrupt any of these memory locations, as it is allowed to directly write to it. Now to protect against such accidental writes or intentional writes, protected mode operating came in. We'll look at protected mode later. Now let's go back to our presentation. Okay, so before we begin assembly language programming, there are a couple of things which one needs to note. Typically, there are two different syntaxes for assembly language: AT&T syntax and Intel syntax. Now, in the assembly language primer for hackers in Linux, we use the AT&T syntax. The Intel syntax is what is typically used on Windows-based assemblers. And this is what we will use for this video series. Now, it is important to note that some assemblers can support both the AT&T as well as the Intel syntax. So it is actually good to know both these syntaxes, as a lot of times code which you might inspect on Linux-based systems might be on AT&T syntax, one on Windows systems would be on Intel. So it's good to know your way through both of these syntaxes. Now what we'll do is, we've covered the AT&T syntax in great depth in the previous video series. So we'll try and understand the differences between the AT&T and Intel syntax, so that from there on we can use the Intel syntax instead of the AT&T one. Okay, some key differences. Now in AT&T syntax, immediate operands are always preceded by the dollar sign. In Intel, they are undelimited. What we mean by that is in AT&T, if you wanted to push L, the value 4 onto the stack, you would have written push L $4. In the case of Intel syntax, you can typically write push 4. Second, the register operands are preceded by the percentage sign, while in Intel they are undelimited. What we mean is whenever you refer to any register, you prefix the percentage sign in AT&T. However, in Intel, you just use the register name as is. Let's come to the next difference. This is a very important one. The order of source and destination operands are typically opposite. In AT&T, you give the order as $4 and %EAX. What this means is add 4 to the existing value of EAX and store it in EAX. In Intel, you would write this as add EAX, 4. This would add the value 4 to EAX and store it there. So don't worry if some of this looks daunting. When we do the actual samples, it will be much more clearer. Okay, some of the other key differences include the size of the memory operand in AT&T is determined typically by the last character. Well, what we mean by this is, if you want to use move in AT&T, typically we would suffix either a B or a W or an L or a Q, denoting the size of the memory operand. So move B would actually move a byte, right? Move W would actually move 2 bytes, so on and so forth. In Intel, we do this by prefixing some keywords like byte pointer, word pointer, D word pointer, and Q word pointer. This is for 1, 2, 4, and 8 bytes, right? So how would this look like? Well, move AL, byte pointer ABC would actually go ahead and take 1 byte from this location and actually transfer it to AL. Some other key differences. When you want to go ahead and refer to memory operands, we basically use the square brackets in Intel, while in AT&T we use the curly brackets, right? So move EAX, bracket EBX is what we would write in Intel. In AT&T, we would actually enclose all the registers we want to refer to as memory operands within the curly bracket. Now there are other small differences here and there which would exist, but we will look at it when we are programming. Just keep these in mind if you've been following the assembly language primer for hackers. Okay, so I guess enough of theory. Let's go on to our customary hello world. Now this hello world program is going to be written in MS-DOS in real mode, right? Which means all the registers are going to be 16 bits in size. Now the whole idea is to work with basic principles and call the MS-DOS interrupt 21 services to print a string onto the screen. Now let's go back to our shell, clear the screen. Now, so how do you go ahead and run programs? Assembly language programs, so how would we run and create programs, assemble them, link them, etc. Well, one of the very easy ways if you want to write programs under DOS is to use a utility called debug. This is an inbuilt utility available on practically every version of Windows. You can just hit debug and you get this small dash here. You can hit a question mark so that you can see various options which you can explore later on. So what we will do in this example is we will create a hello.com executable program. This would be a COM executable, and this executable will print hello world on the screen, right? So let's go ahead and do this. Now, one of the things which you need to remember is, in case of a COM file, the executable code starts from the 100th offset from the beginning of the file. So what we'll do is we'll use the -a, which is start writing assembly at a location 100 from the beginning of the file. Now in case of a COM file, the first instruction is always a jump to the actual code. Now in this case, what we'll do is we just give an arbitrary position for now. I'll come to why a little later. Now let's go ahead and store the string hello world. How can we do that? Well, we can just use db, define byte as you know, give the exclamation mark, also the $, which acts as a delimiter. Now what we need to do is, ideally we would want that the hello world should be printed. So for this, we need to invoke an appropriate system call. Now in case of DOS, the way to do is actually to invoke an interrupt called interrupt number 21. Now how would we do that? Well, before we call that interrupt to print hello world on the screen, the first thing we need to do is move the memory location of where this hello world string is stored into the DX register. Now we just have to mention the appropriate offset, which is 0103. This is sufficient. Then interrupt 21 can do a lot of things. So we have to specify exactly what it needs to do. What we want is to print the string pointed to by DX on the screen. For that, we need to move the value 900 into AX. Actually, you just need to move 9 into AH, which is the 16-bit high register of the 8-bit high register of the 16-bit AX register. But we can even do it this way, there is no harm. Now we call interrupt 21. After this, we want to exit the program, which you can easily do by calling interrupt 20. Okay. Now here is something interesting. So the program will start running, first hit the jump statement, which should actually take it to this location, right? And from here on, the code will start executing. However, we have just written jump 1, 2, 3, 4 in the beginning, simply because at that point we did not know how much space hello world would take. So let's modify just the first statement. So let's go back there and actually add a jump, and then we give the actual memory location, which is 0110, right? And we are done. Now just to verify, we can actually do a unassemble at location 100. Now this will show us the code which we have right now entered. Now if you note, the first instruction is a jump to 0110. If you try to look at it here we are. What this does is moves the value 0103 into DX, right, which is where actually our string is located, which is here, and from there on the execution starts. So what we need to do now, and if you want to look at a hello world string, actually we can hit D. So this will start disassembling from the same point, and you can notice the hello world string is here. Now the first thing we need to do is save all this code into a COM file, or create a COM file with this code. Now to do that, we first need to figure out the size of the COM file. So we started writing our code from offset 0100 and ended here 0118, right? So let's try and find the file size. For that, you can use the H command and give it the final value, which is 11A, which is what we have here, and then the initial value, which is 0100. Now interestingly, this gives us both the sum as well as the difference of these two numbers. So let's take the difference, which is 001A. Now we have to create a name for the file. We use the N command for that and give it a hello.com name. Now we need to figure out the amount of bytes we write, which we've already figured out, which is 001A. Now, before you actually instruct debug to write, you need to load the number of bytes to write from the current stream into the CX register. For that, we use the command -r CX. So here we can enter 001A. That's also there. Now to write all this code which we created onto hello.com, we use the W command. So it says written 1A bytes. This is the actual amount we had loaded. Now we can quit debug, and just here we can just type in hello.com, and if you notice, it printed hello world, right? Let me clear the screen so that you can have a look again. Here it is. Have your hello.com, and that's printing hello world. Right? Awesome. Now, one of the other things which you can also do with debug is load an executable and actually disassemble it. So I've loaded hello.com, and I can just use a disassemble. This is dumping the entire executable, but I can also use a U, which stands for unassemble or disassemble, and we'll be able to actually see our original code. So if you notice, there's a jump statement. From here on, we have our move dx 103, etc. And this part in between is actually the hello world string which was written. Unfortunately, debug cannot differentiate between data which we fed in with respect to the actual executable code. That's why, unfortunately, it has disassembled all these values, and these in between ones don't make any sense, right? Okay, perfect. So I'll leave it at this. Try this example out. This is probably the only example we will look at as far as coding in DOS is concerned, because purely from today's current perspective, it isn't of much help, right? Unless you still want to play around and write TSRs, which are terminate and stay resident programs, where you can do a lot of fun stuff, like writing small keyloggers for DOS, etc. But apart from that, I mean, there isn't much of great use I can see, at least at this point, for doing assembly in DOS anymore, that too in real mode. So try this out. Thank you for watching this video. Hope you liked it. Please leave your comments behind as to what else you would like to see. As I've told you repeatedly in each video, it's just your comments and your encouragement which makes me go further and create more and more videos. So looking forward to hear from you. Have a great day ahead. Bye-bye.